Hello students, welcome to the one short video on module 1 which is all about PN junction diode. So let us take the topics one by one. So the first topic that comes is that what is a semiconductor? So we all know, as the name itself implies, semi means half conductor. That means these are those special class of elements whose conductivity lies between that of insulator and conductor, meaning that their conductivity is higher than that of insulators and lower than that of conductors. So the conductivity lies between conductors and insulators. So those are called semiconductors. The most popular semiconductors that you have studied are silicon, germanium. And if we want to say, or if we want to tell that which one will we prefer the most, then we will prefer silicon the most. That means out of silicon and germanium, we are going to prefer silicon. Reason is that, the reason being, the first and the foremost important reason is that silicon has less leakage current than that of germanium. And what is the reason for it? For having less leakage current? We all know that silicon has atomic number 14. Germanium has atomic number 32. So the configuration becomes in the shell. That means the number of electrons in each shell, that particular configuration becomes 284 for silicon, and for germanium it is 2, 8, 18 and 4. This is how we write the configuration. So now, the as we all can see, the valence electrons of germanium are in fourth shell, whereas the valence electrons of silicon are in third shell. That means the force of attraction between nucleus and valence electrons is more for silicon than compared to germanium. So what happens is, when we will supply a very less amount of energy in the form of heat to both the semiconductors, then in case of germanium, the valence electrons will get free very easily because they are lying in the fourth shell, having less force of attraction between them as well as nucleus. So they will become free very soon. So the current that will be generated will not be proportional to the energy. That means we are supplying less energy, but we are getting very high current, which is not desired. Okay, so what happens is, this particular unwanted current is called leakage current, and this leakage current is lesser in silicon as compared to germanium. So this is the first and the foremost reason why you prefer silicon as compared to germanium. Okay, now the second reason comes that silicon is more stable at higher temperatures, whereas germanium becomes unstable at higher temperatures. So silicon is more stable at higher temperatures. This is the second reason. And the third reason is that silicon is abundant on Earth. That means it can be found very easily and in large amounts on Earth. So that is why we prefer silicon. But I hope and I advise you all that you write the reasons for preferring silicon in the same order as we have written over here. The first and the foremost reason is that the silicon has less leakage current. The second reason is that it is more stable at higher temperatures. And the third reason is that it is abundant on Earth. So that is why we prefer silicon over germanium. Now let us move forward. Another topic comes is types of semiconductors. So what are the types of semiconductors? They are divided into two parts, that is intrinsic and extrinsic. Intrinsic is the pure form, That means when you do not add any impurity to a pure semiconductor and it is in its purest form, then it is called intrinsic. And when you add impurity to a pure semiconductor, then the resulting semiconductor is called extrinsic. And depending upon the type of impurity that you are adding, the extrinsic semiconductor is further of two types, that is p-type, n-type, where p and n does not have any full form. P-type semiconductor is formed when you add trivalent impurity to a pure semiconductor. Trivalent means having 3 valence electrons, which are group 13 elements. And group 13 elements examples could be indium, boron. These are the group 13 elements examples, which can be added as impurity to a pure semiconductor. For n-type semiconductor, you add pentavalent impurity. And pentavalent impurity means having 5 valence electrons, which are group 15 elements in the periodic table, and examples are phosphorus, antimony, and so on. So these are the classifications of semiconductors. All right. Now, in the case of p-type semiconductor, the very important thing that we all should remember is that the majority carriers are holes, minority are electrons, and the ions which are formed, because trivalent impurity is acceptor impurity, because in the case of trivalent impurity, 3 of the electrons, because it will be having 3 valence electrons, so these 3 electrons will be forming the covalent bonds with the 3 electrons of silicon or germanium in whatever semiconductor you will be adding it. All right. So in this particular case, the ions, that means this trivalent impurity is acceptor impurity, has always the tendency to accept the electron. So the charge that it will acquire will be negative. So the ions will be negatively charged. Negative ions. All right. In the case of pentavalent impurity is donor impurity. That means it has the tendency to donate the electron. So therefore, it will be always having positive charge. So in the case of n-type semiconductor, you must remember that the majority carriers are electrons, minority are holes, and the ions are positively charged. All right. So these things are very, very important to remember whenever we come across p-type and n-type semiconductors. Whenever we come across p-type semiconductor, the first thing that should come to our mind are these 3 points, that the majority carriers are going to be holes, minority electrons, and the ions will be negative. Whereas for the n-type semiconductors, majority electrons, minority holes, and the ions are going to be positive. So these are the main important points about p and n-type semiconductor. Now let us move forward, and the next topic that comes is p-n diode. p-n diode, that means when you will be joining the p and n semiconductor by special fabrication techniques, then the device that is formed, that is called p-n diode, semiconductor diode, or junction diode. So it has various names, and all of them are the synonyms of each other. So this is p-n diode, and the diode word comes from the fact di means two, ODE means, this word ODE has come from electrodes. So this part is anode and this part is cathode. The conventional direction of flow of current is from P to N, that is current flows from anode to cathode. So this is p-n diode. Why is it called junction diode? Because this is junction. As you can see, I am highlighting this. This is junction. Junction means that particular point of contact where p and n semiconductors are joined to each other. So that is called junction. That is why it is also called junction diode. Now, from here comes two different terms. They are depletion layer and potential barrier. So what is depletion layer? Depletion layer is basically a layer or an area which is formed near the junction. And how is it formed? When you join P and N semiconductors, holes, P have majority of holes, N has majority of electrons. So when a device is becomes one, when you have joined P and N semiconductor, now this device has become one. Now what will be the tendency? That the tendency will be that due to the concentration difference. What is the concentration difference? That on one particular side we are having majority of holes, and on one particular side we are having majority of electrons. So a diffusion process will start. Diffusion means movement from higher concentration region to lower concentration region. That means the holes from p type will move towards n type, and the electrons from n type will move towards p type. And in this particular process, when the near the junction, when the holes and electrons will collide with each other, or they will combine with each other, what will happen? When a hole and an electron will combine with each other, they will become neutral and they will disappear. Energy will also be released in the form of heat or light. So two process comes into light when recombination takes place. When recombination takes place, that means when electron and hole combine, so two things occurs. One is that both of them disappear. Electron and hole disappear. That means they become neutral. Now you are not left with any free electron or any hole. And the second thing that comes into light is that energy is released. And this energy can be in the form of heat or in the form of light. It can be in any form. So these two things happen when recombination takes place. So near this junction, the recombination is maximum. And when the recombination is maximum, the electrons and holes disappear, thereby leaving behind the ions. So here, only ions will be left. On the p side, we will be having negative ions, and on the n side, we will be having positive ions. And around these ions, we are not having any charge carriers. So a particular area like this is formed. And this depletion layer, when it is formed, holes, it will now, these positive ions of n type, as you all can see, these will repel the holes that are coming from p and trying to enter into the n. So now they stop the further diffusion process. This particular layer is opposing the further diffusion process. Similarly, the electrons that are trying to come from n to p type, or they are trying to enter from n type to p type, they will be repelled by the negative charge of the depletion layer, or the negative ions that are present in the depletion layer. So what is depletion layer? Basically, depletion layer is the layer near the junction. Layer near the junction. One thing, you must write this down, that it is the layer near the junction. Second thing, that does not contain any charge carrier. That means you need to tell that it does not have any charge carrier. Any charge carrier. Now you must tell that what does it contain then. So it contains only immobile ions. This is the third thing. And the last thing that you must tell in the definition of depletion layer is that it opposes the further flow of charge carriers across the junction. All right. So these four points must come into the definition of depletion layer. First of all, you must tell that this is the layer near the junction. Then you must tell that what is absent in it and what is present in it. It is very, very important to mention that it does not have any charge carrier, because the word depletion means, when you will search it in the dictionary, you will be knowing that depletion means an area where there is a lack of something. That is the meaning of depletion. All right. So depletion means the area where something is lacking. So here the charge carriers are lacking. That means they are not present. So you must mention that it does not contain any charge carrier. It contains the mobile ions, third thing. And fourth and lastly, and the most important, that it opposes the further flow of charge carriers across the junction. So when you will join all these 4 points, the depletion layer definition will be completed. All right. Now another definition that comes along with it, that is potential barrier. Now what is potential barrier? As you can see, the word is potential, and potential is somewhere related to voltage, and voltage in turn is related to the electric field. All right. So this is how we remember it. Potential is related to means voltage, and voltage is related to electric field, because in 12th we all have read the formula E is equal to V by L. That is, electric field is equal to voltage upon L. So here, when the electric field has come over here, now what is the definition? Again, look into the depletion layer. Here, in the depletion layer, you all can see that we have oppositely charged ions nearby residing. All right. So an electric field will be developed between these oppositely charged ions. And what is this electric field? The function of this electric field is again to act as a force which is opposing the further flow of charge carriers across the junction. So the depletion layer and potential barrier are doing the same thing. That is, they are opposing the further flow of charge carriers across the junction. But while mentioning the definition for the depletion layer, you must mention that this is a layer near the junction which contains ions and does not contain the charge carriers. But while mentioning the definition for potential barrier, you must write down that this is the electric field which is developed in the depletion layer, or which is developed near the junction, and which opposes the further flow of charge carriers across the junction. All right. So this is how we mention the definition for the depletion layer and potential barrier. I hope it is clear to everyone. So potential, what is potential barrier? Electric field developed between oppositely charged oppositely charged ions near the junction, which opposes the further flow of charge carriers across the junction. So that is what is potential barrier. And we all must remember potential means voltage. So for silicon, the value of potential barrier is 0.7 volt. We must remember it. And for germanium, it is 0.3 volt. You also must remember the units. All right. So this is what is all about depletion layer and potential barrier. Now let us move to the another topic, and that is biasing. Now we are going to connect the battery. So the process of connecting battery to any circuit, that is called biasing. It's not only about PN junction diode, but when you connect the battery to any electronic circuit, that is called biasing. This process is called biasing. And because there are two ways of connecting batteries, because either a battery has positive and negative terminal. So either you can connect the positive terminal first, or you can connect the negative terminal first. So there are two ways of connecting the battery. On this basis, we have forward and reverse biasing. All right. So for the forward biasing, if we talk about forward biasing, what is forward biasing? When you connect, this is the symbol of PN diode. All right. So when you connect the positive part of the battery to the P type and negative part to the N type, that is called forward biasing. And when you connect the positive part of the battery to the N type and negative part to the P type, then that is called reverse biasing. All right. So this is reverse biasing. I have shown both of them. This is forward biasing and this is reverse biasing. Now the key points that we all must remember while these terms we come across these terms. In the case of forward biasing, current is due to majority carriers, and because the word itself implies majority means that are more in number, so the current in the case of forward biasing will be maximum. So here the current is due to majority carriers. I have explained into very depth in my video which I have made specifically on biasing, so you can refer that also in the playlist. And here also I'm giving an overview because this is a one short video, so we must remember only the important points. So I'm not going into much deep, but these are the very key points that we must remember. So whenever we come across forward biasing, the things that should come into our mind is that the current is always due to majority carriers for the forward biasing, and therefore current is maximum. And when the current is maximum, resistance is minimum. That means forward resistance is less. All right. Depletion layer decreases in the case of forward biasing. So these are the important points that we must remember. And also in the case of forward biasing, as you all can see, we have connected the battery and the current will start flowing. But this current will only start flowing when this battery value which we have connected, which I am ticking, this battery value exceeds the value of potential barrier. That means, for example, you have made the diode of silicon. All right, this diode is made up of silicon. Now, silicon has a potential barrier 0.7. So 0.7 potential barrier means, see, let us take a simple example. If somebody is pushing you and you want to push him in the opposite direction, so what you will have, what you will do, you need to apply a force first of all in the opposite direction, and the minimum force that you must apply must be equal to or greater than the force that has been applied to push you. All right. So in the similar manner, if you want to make the current flow, the current will only flow when this battery value will exceed or at least equal to the potential barrier. So if the silicon diode is used, so the potential barrier will be 0.7 volt. So the battery value, when this battery value will exceed more than 0.7 volt, only then the current will start flowing and the current will be maximum. All right. So here we must remember these points. So it must exceed the potential barrier. Now let us come for the reverse biasing case. In the case of reverse biasing, first of all, current is due to minority carriers. And because it is due to minority means which are lesser in number, that means the current is going to be very less. So the current here is minimum. For the ideal case, it will be 0, but for the practical case, it will be minimum. And therefore, resistance is maximum. And here the depletion layer increases. All right, so these are some of the points. Another point about reverse biasing is very, very important. That is the current which flows over here, that is called reverse saturation current. Why the word saturation has come? The word saturation has come because as soon as you will reverse bias the diode, whatever small amount of current is going to flow, it will flow at once. That means it will attain its maximum value quickly. Whatever the current has to flow, it will flow at once and it will then become constant. That means when you will keep increasing the reverse voltage, the current is not going to increase. It will become constant. Once it has flowed, so now it will become constant. Now, But a certain point comes when it will be increasing, and that is called breakdown voltage. So I will show that particular current in the characteristics. So we will learn it over there. But one important thing that we should remember here itself, that reverse saturation current is constant with the voltage but depends upon the temperature. So here the current is not dependent upon the voltage. In fact, it depends upon the current. Sorry, it depends upon the temperature. And as temperature increases, this current also increases, because when temperature increases, covalent bonds break, carriers come out, and both the types of carriers will come out, that is majority along with the minority. So minority carriers when will increase, so current will surely increase. So this current is not dependent upon the voltage. In fact, it is dependent upon the temperature. So when temperature will increase, this current will also increase. Now, let us move on to the very important topic, which is very probable or very important, and it might come in your final semester exams, VI characteristics of PN diode. So whenever we talk about characteristics of any circuit, it is basically a graph between voltage and current. So voltage is always on the x-axis, current is on the y-axis. So here in this particular direction, upward direction, I will be drawing the forward current, and the reverse current is opposite. Therefore, I will be drawing that current downwards. Reverse current is lesser, so the unit will be microampere. And here, this is forward voltage, this is reverse voltage. All right. Now, let us see the case of forward biasing. We already told that, for example, this is the potential barrier or the knee voltage. Knee voltage 0.7 for silicon, 0.3 volt for germanium. So till the knee voltage, current will be negligible. But after, as soon as the battery value, means this particular voltage, exceeds the potential barrier, the current will rise rapidly and it will increase. All right, so this is the case for the forward biasing, and that's all for the case of forward biasing. In the case of reverse biasing, as I have told, saturation means whatever current will flow, a very small amount will flow, and whatever it needs to flow, it will flow at once. So as soon as you will reverse bias, a very small current flows, and now it becomes constant with the voltage. As you are increasing the voltage, current is not affected due to it, and but a certain value comes, that is called the breakdown voltage, at which the junction collapse and the depletion layers which was stopping the current to flow, that breaks, that collapse basically, and the carriers move and cross the junction, and thus the reverse current increases. So at this particular voltage, reverse current increases. So this is the VI characteristics of PN diode. Very important, but you must understand them logically. All right. Now here another thing comes is diode current equation. We all must know diode current equation. Diode current ID is equal to reverse saturation current I naught or IS, however you can, any of the ways you can represent it, into bracket e raised to the power V is the applied voltage, upon eta is a constant, 2 for silicon, 1 for germanium, Vt is the thermal voltage. Formula is Kt by Q. Where K is the Boltzmann constant. Value is 1.38 into 10 raised to the power minus 23 joule per Kelvin. T temperature will be always taken in Kelvin. So if temperature is given in degrees Celsius, you can convert it into Kelvin by adding it to 273, and Q is the charge, that is 1.6 into 10 raised to the power minus 19 coulomb. So the equation is E raised to the power V upon eta Vt minus 1. Minus 1 is not in the power of E. It is downwards. Alright. So I naught is the reverse saturation current. And V is the applied voltage. So this is the diode current equation, very important, which relates the diode current and the diode voltage. Alright, so this is a non-linear equation. So that is why in the graph, in the case of forward biasing, when we said that the current increases, so we could have drawn a straight line also, but we have drawn it in the form of a curve. As you can easily see that the current is rising exponentially. So this is due to this particular equation. Alright, so let us move forward now. After the VI characteristics, if we talk about, so these VI characteristics are for practical diode. If we want to draw the characteristics of ideal diode, so which is very simple, in the case of ideal circuit, we talk only in two terms, that is either zero or infinity. So when we are saying that the current is maximum for forward bias, that means current is infinity for forward bias, and we need not consider any potential barrier also. For the case of reverse biasing, the current is zero because it is minimum practically. Alright, so this is the current parameter, voltage. So these are the ideal diode characteristics. So we can even draw like this if we are asked about ideal diode. Now let us move forward, and the next topic that comes is breakdown voltage. Breakdown mechanism. As I have already told you in the characteristic part, that when you keep on increasing the reverse voltage, a point comes when the junction collapses, and at that particular point the reverse current rises sharply. So this voltage is called breakdown voltage. Now in the next topic, that is breakdown mechanism, we are going to see that what are the mechanisms which makes this reverse current to rise sharply. So breakdown mechanisms. So these breakdown mechanisms are of two types. One is Zener breakdown, another is avalanche breakdown. Alright, Zener breakdown, avalanche breakdown. So what is Zener breakdown? Basically, Zener breakdown mechanism occurs in the diodes which are heavily doped. So you must write down occurs in heavily doped diodes, and avalanche occurs in lightly doped diodes. Alright. Zener breakdown mechanism occurs at voltage less than or equal to minus 5 volt. Minus sign will be always there because this is in the reverse part. So in the case of reverse voltage, battery is negative. Alright, avalanche breakdown takes place at a voltage greater than minus 5 volt. This is another difference. Next difference is that Zener breakdown, why the Zener breakdown occurs. So Zener, as you will keep on increasing the reverse voltage, we all know along with the voltage, electric field also increases. So in this case, the electric field becomes so strong that it breaks the covalent bonds and the current increases. So here, the electric field plays the main role. Strong electric field. Alright, whereas for the case of avalanche breakdown, as you will keep on increasing the reverse voltage, the electric field also increases, but here the electric field is not so strong. Now what happens here is when you will keep on increasing the reverse voltage, the velocity of the minority carriers increases. Alright, and when the velocity increases, kinetic energy increases because kinetic energy is half mv squared. And when the kinetic energy increases, what happens is when the kinetic energy increases, so this particular thing is like that. For example, when a fast moving uh, particle collides with a stationary particle, so it transfers its kinetic energy to that stationary particle, and it what happens is that the covalent bonds will break and the electrons will come out, or the carriers will come out, electrons as well as holes, and the current will increase. So in the case of avalanche breakdown, velocity will increase, kinetic energy will increase, and due to that covalent bonds will break. Whereas in the case of Zener breakdown, electric field is strong to break the covalent bonds. Another difference is that Zener breakdown has a sharp curve, whereas avalanche breakdown is a multiplication process and therefore it has a gradual curve. Multiplication process means when the velocity increases, kinetic energy increases, covalent bonds will break. So this process will repeat for the uh, outcoming charge carriers also. The carriers which will be generated will follow the same process. That means their velocity will also increase, kinetic energy will increase, and hence they will result into the breakage of the covalent bonds. So these are some of the differences between Zener and avalanche breakdown. The last difference is like Zener breakdown has negative temperature coefficient. When the word comes negative, that means inversely proportional. And what are inversely proportional? Vz, that means the breakdown voltage is inversely proportional to temperature. As temperature will increase, breakdown voltage will decrease. In the case of avalanche breakdown, it has positive temperature coefficient. That means the temperature and breakdown voltage are directly proportional. That means as temperature will increase, breakdown voltage will also increase. So this is the difference between Zener and avalanche breakdown. Alright, now let us move on to the Zener diode. One thing I must tell you that Zener diode and Zener breakdowns are two different things. Zener breakdown was a mechanism and Zener diode is a diode. And this diode is specially designed to work in the breakdown region. That means means that it can work normally in the forward bias as a normal PN diode. It can also work in the reverse bias region, but it is mainly designed to work in the breakdown region. So, in the case of Zener diode works as a normal PN diode in the forward bias region. As a normal diode in forward bias region. But it is mainly designed to work in breakdown region. Very, very important thing. All right. So if I draw the characteristics of Zener diode, it will be having same characteristics as that of a normal PN diode in the forward bias. Whereas in the reverse bias also it will be having somewhat same characteristics, but it is mainly designed to work in this particular region that is called breakdown region, having some breakdown voltage which is generally -5 volt. And here we all can see that the special thing about breakdown region is that here the voltage is constant at every point. As you can see, voltage is constant at all the points. But what varies is current. So current varies from Iz minimum to Iz maximum. And if the current exceeds Iz maximum value, then only the diode will be damaged. That means breakdown does not mean that the diode is damaged. All right. The diode will only be damaged if the current flowing through it exceeds the Iz maximum value. So this is the characteristic of Zener diode. Now let us see the symbol of Zener diode. This is the symbol, or simply you can draw it like this way also. This is the symbol of Zener diode. All right. So it is mainly designed to work in the reverse or the breakdown region, but it will work normally or fine in the forward bias region as well. All right. So now the main application of Zener diode is shunt regulator. Zener diode as shunt regulator. We all know that the Zener diode is mainly designed to work in the breakdown region. And what we have seen, that what was the special thing of the breakdown region? That voltage at each point is constant and only the current varies. So when the voltage is constant, so if we put this constant voltage device in parallel with a load resistor, all right, and we connect a battery in order to limit the current flowing from the battery, what we are doing? We are putting a series resistance Rs. So if we connect a constant voltage device in parallel or in shunt with a load resistor RL, so the voltage across this RL will be also maintained constant. That is why it is called regulator, because it is generating constant voltage. All right. And because it is in parallel with the load resistor, that is why it is called shunt. So this is the main application of Zener diode, that it acts as a shunt regulator. Now in order to study the numericals, we are having three numericals related to it. So that is case 1, when we will be giving the fluctuations in Vi and we will keeping RL fixed. Second, we can keep the Vi fixed and RL variable. And thirdly, we will keep both of them fixed. That means Vi, RL both will be fixed for the first case. Case 2, Vi variable but RL fixed. Because what does a regulator means? That despite the fluctuations in the supply voltage, that is Vi, or load resistor, the voltage is constant. That is what a regulator means. All right. So we will be giving the fluctuation in Vi once and we will be giving the fluctuations in RL once. So Vi fixed, RL variable. So all the numericals which are related to these three cases, I have discussed in a very detailed manner in my videos. I will be sharing the links in the description box. So please refer them, because those videos are specifically for these numericals. If I will be doing it over here, then it will be a very long video, and I will be repeating the same thing again and again. So all you can do is, if you have reached up to here in this particular video, and you want to study the numericals related to first, second, and third case, you can directly go to the description box and refer the link that I have given for the numericals on the Zener diode, and you can refer those links. So you will be directly getting the numericals from there. So do them if you want to practice them for your exams, you can do it from there. So Zener diode as shunt regulator. So important thing is, you must know what is a Zener diode. Secondly, you must know the characteristic. You must know the fact that Zener diode works as a normal PN junction diode in the forward bias, and you must know the major application of Zener diode, that is a shunt regulator. All right. Now the next topic that comes is rectifiers. And what is a rectifier? Rectifier converts AC into DC, pulsating DC. All right. Now rectifiers are of two types, half wave rectifier and full wave rectifier. And full wave rectifier are of further two types, that is center tap rectifier and bridge rectifier. All right. So if we talk about half wave rectifier or any rectifier, we know that rectifier converts AC into DC. So we must get AC, and for getting AC, we must have a transformer. So we have a step down transformer from where we will get the AC. And if we are going to draw the half wave rectifier means the circuit will be only having one diode, and we will be calculating the output voltage across this RL. All right. And this VI will be here, input voltage, which is in the AC form. So the input voltage is in the AC form, and in the output you will be getting DC. So this is the input voltage. This is AC. All right. Now for how do you analyze the circuit? First of all, this is the positive half cycle. All right. So you put here plus and here minus. VI upar plus, niche minus. All right. So you have to put the signs like this. Now, as you all can see that the diode is forward biased because P is getting positive sign and the N is getting negative sign. So what happens over here is that diode is forward biased. So assume it as an ideal diode and replace it with a short circuit. All right, that means a simple wire. So when you will replace it with a simple wire, now your objective is to calculate V naught. V naught can be calculated by applying KVL in this particular loop. Apply the KVL, and you, after applying the KVL, you will get V naught is equal to VI for the positive half cycle. Now again, during the negative half cycle, what you will do, you don't have to struck off these signs. In the brackets you put minus and plus because this is the negative cycle. Now what happens is diode will be reversed. Reversed means no current, zero current. That means open circuit. Open circuit means you remove the diode and do not replace it with a wire. Leave the connection open. All right. When the connection will be open, that means the current in the circuit will be zero. No current in the circuit. That means no current in RL, and you will be not having any V naught because V naught is IRL. I is zero. Therefore, IRL is zero. So V naught is zero in this case. Now let us draw the output. Let us separate first of all the cycles, positive cycle and negative cycle. Here we write V naught omega t. Positive cycle, answer is V naught is equal to VI. See the VI upward and draw it in the same manner. Negative cycle, for the negative cycle you have V naught equals to 0, so draw V naught 0. Again for the positive cycle you have VI, so draw it as upwards. All right, so this is the half wave rectifier. Now full wave rectifier. In the case of full wave rectifier, first of all we have center tap rectifier. Center tap rectifier, the special thing about center tap rectifier is that you have double secondary windings over here as compared to primary. So you need not count and draw, you just draw more number of secondary turns. All right, and you connect the load resistor in between. That means you have tagged the circuit from the center. That is why the name comes center tap. Two diodes like this are connected, D1, D2, RL, V naught will be calculated over here. Polarity taken will be like this and like this. So you must have a transformer in the case of rectifier because you are going to convert AC into DC. So AC will only come from the transformer. All right, so we always need to have a transformer over here. Now during the positive, again, let's draw the input waveform first. We have an AC waveform. In the output, let's create the space And let's analyze the circuit now. So for the positive cycle, we will put now here in the case of center tap, the special thing I told you that this transformer is having double turns in the secondary windings. So here the VI will be divided in two parts because twice of VI will be induced in the secondary winding. So we have divided 2 VI into two parts, VI upward and VI downward. Now for the positive cycles, the signs will be like this. So we can see that D1 is forward, D2 is reverse. D2 is reverse means D2 is open. That means no current will flow in the downward circuit or loop. So the current will flow in the upward loop, and when we will calculate V naught by applying KVL, we will be getting V naught is equals to VI. Similarly, for the negative half cycle, we will put the signs like this. In this case, D1 is reverse, D2 is forward now, and now again by applying KVL, you will get in either direction you can apply the KVL, you will get V naught again equal to VI. Alright, now let's draw the output. So for the positive cycle, answer is VI. VI will be drawn as it is drawn upwards. Now for the negative cycle, again you have answer V naught is equals to plus VI. Here it is minus VI. If you see upwards, it is in the case of input voltage, it is minus VI. If you need to convert it into plus VI, you have to fold it upwards. That means it will be like this. Again, for the positive cycle, you have V naught equals to VI like this. So this is a full wave rectifier, and as you can see, full wave rectifier is rectifying both the half cycles, that is the negative and the positive half cycle, whereas half wave rectifier was rectifying only the positive half cycle and it was not giving any voltage in the negative cycle. So this is the difference between half and full wave rectifier. Now, the one we prefer most is the bridge rectifier. For the bridge rectifier, again we will draw the transformer, but this time the transformer is ordinary. That means secondary and primary number of turns are equal. And here the diodes, we will be having 4 diodes. Start connecting them. Direction of diodes is very, very important to remember. So this is the diagram of bridge rectifier. We have 4 diodes over here. Again, we draw the input. All right. So for the positive half cycle, we put the signs like this. And as we can see, diodes from here, that D2 and D4 will be forward biased, and D1 and D3 will be reverse biased. D1, D3 will be reverse biased. All right. So in this case, when D1, D3 will be reversed, that means they will be replaced by open circuit, and D2, D4 will be replaced by short circuit. So when you will apply the KVL in the loop, because the current will flow in this particular way, I will draw the equivalent circuit for this particular case. Here was D1. D2 was forward, that is why I replaced it with the short circuit. D4 was also forward, that is why I replaced it with the short circuit. D1, D3 were reverse. So this is how we have the equivalent circuit. Now the current will flow like this. The current will not go into the open circuit part, it will directly go over here. Again, it will not get divided because open circuit, it will not go into the open circuit, and the direction of the current will be like this. So in the same manner, you apply the KVL and you will be getting V naught equals to VI. Similarly, for the negative half cycle, same will be the case. You draw the equivalent circuit, and When you will put the signs over here, that is minus and plus, you will be seeing that D1, D3 this time will be forward biased and D2, D4 will be reverse biased. So again, you can draw the equivalent circuit in the same manner and apply the KVL. You will be getting V0 is equals to Vi. Now, in order to draw it for the positive part, we have Vi again. For the negative part also, we have V0 equals to Vi, but this is minus Vi, so we need to fold it upwards and Vi. So the output waveform will be the same in both the case, that is center tapped and bridge, but the process of working will be different for both the circuits and both have their own advantages and disadvantages. So out of center tap and bridge, we prefer bridge rectifier. The reason is that in the case of center tap rectifier, you have seen that the transformer is having double of the secondary number of turns. So that is why the transformer here will be costly. Also, the diodes in the center tap rectifier are costly because the PIV, that is the peak inverse voltage, that is the amount of voltage that a diode can tolerate, is more for the center tap rectifier. So that is why they will be costly. So the diodes and transformer are costly for center tap rectifier, whereas for bridge rectifier, they are economic. So we prefer bridge rectifier. All right. So that was the working of center tap and bridge rectifier. Very important, and this question has come many a times in the exams, that explain the operation of bridge rectifier with input and output waveforms. So you have to properly explain the circuit diagram working and the input and the output waveforms. Now, after the working of rectifiers, let us see the efficiency, ripple factor, and all these things of rectifiers. These are very important and they can come in the final exams also. So first of all, directly we have to learn the values of VDC, VRMS for both the rectifiers. So first of all, let us take half wave rectifier. For half wave rectifier, VDC is equals to Vm by pi. Alright, I have derived this particular formula or this particular value of VDC in my video, but for the exams point of view, you can directly learn these values because the derivation hardly comes in the exams. So we can directly learn VDC is equals to Vm by pi, and IDC therefore will be Im by pi. So that means current and voltage are analogous to each other. If VDC is Vm by pi, then IDC will be Im by pi. Similarly, VRMS for half wave rectifier is Vm by 2, and therefore IRMS is Im by 2. Okay, so voltage and current go analogous to each other. So if VDC is Vm by pi, IDC is Im by pi. If VRMS is Vm by 2, IRMS is Im by 2. Now for full wave rectifier, VDC is equals to 2 Vm by pi. Therefore, IDC will be equals to 2 Im by pi. VRMS for full wave rectifier is Vm by root 2. And IRMS is Im by root 2. So these values should be on our tips, that what is VDC for half wave, what is VDC for full wave, what is VRMS for half wave, and what is VRMS for full wave. Alright, so these are the values for full wave rectifier. Now the first parameter that we should know to calculate is ripple factor. And for ripple factor, first of all, we should remember the mathematical expression to calculate the ripple factor. So the mathematical expression for ripple factor is under root VRMS upon VDC whole square minus 1. This is the mathematical expression of ripple factor. When you will put the values of VRMS and VDC for whatever rectifier you want to calculate the ripple factor, you will be getting a fixed value because VM will get cancelled out, and you will be getting a fixed value for the ripple factor, either for half wave rectifier or for full wave rectifier. So if I want to calculate the ripple factor for half wave rectifier, I will apply the same mathematical expression. I will put the value of Vrms. Vrms for half wave rectifier is Vm by 2. Vdc is Vm by pi. I will put these values Vm by 2 divided by Vm by pi whole square minus 1. Now it comes out to be Vm square by 4 into pi square by Vm square minus 1. So it becomes pi square by 4 minus 1. And the answer, when you will solve it through your calculators, you will get 1.21. So the ripple factor for half wave rectifier is 1.21. Similarly, for full wave rectifier, using the same mathematical expression and putting the values of Vrms and Vdc, what will be the value of Vrms for full wave? It will be Vm by root 2 and Vdc is 2 Vm by pi. Using the same mathematical expression of ripple factor, that is Vrms upon Vdc whole square minus 1 under root, you will be getting 0.48. So you must know how to calculate the ripple factor for the half and full wave rectifier, because this question is very important from the exam's point of view. Now the second thing that we should know how to calculate is efficiency. See, generally the efficiency is output upon input. So rectifier converts AC into DC, output will be in the DC form. So therefore DC power upon AC power into 100, because efficiency is generally calculated in percentage. Alright, so DC power formula is I square R. If it is DC power, IDC square RL, and if it is AC power, it will be IRMS square RL. So this is the general formula for the efficiency percentage. Very easy to remember. Now if you want to calculate the half wave rectifier efficiency, then we all know that VDC for half wave rectifier is Vm by pi, and therefore current, that is IDC, is equals to Im by pi. Similarly, IRMS for half wave rectifier is Im by 2. Therefore, eta percentage is equals to IDC square RL, that is Im by pi square RL, divided by IRMS square RL, that is Im by 2 square RL into 100. This is the formula. Now Im will get cancelled out and you will be left with 4 upon pi square. RL will also get cancelled out, and when you will solve this expression through your calculator, you will be getting 40.6%. So we must know how to calculate the efficiency of half wave rectifier. Similarly, for full wave rectifier, applying the same mathematical formula for the efficiency, that is IDC square RL upon IRMS square RL into 100, and putting the values of IDC and IRMS for full wave rectifier, that is IDC is equals to 2 Im by pi and IRMS is equals to Im by root 2. Putting both these values, you will be getting eta percentage is equals to 81.12%. So this is how we calculate the efficiency. The next thing that we must know about the rectifiers is the peak inverse voltage, which is also shortly termed as PIV. PIV. Peak means maximum, inverse means reverse voltage. That means the maximum reverse voltage which a diode can tolerate, that is called PIV. So in the case of half wave rectifier, we can remember it as it is. In the case of half wave rectifier, the diode PIV is only Vm. That means the maximum voltage of the AC. Similarly, for full wave rectifiers were of two types, that was center tapped and bridge. So in the case of center tapped, the PIV was, for each diode, the PIV is 2 Vm, and that is why the diodes were costly in the case of center tapped rectifier, because they can withstand a large voltage. All right, so they were costly. Transformer was also costly in center tapped, and that is why we preferred bridge rectifier, because it was economic. In the case of bridge rectifier, we had 4 diodes, and PIV of each diode is simply Vm. So for half wave rectifier and for for bridge rectifier, PIV of each diode is Vm, but for center tap it is 2 Vm, and that is why it is costly. All right, so this is the case of rectifiers. So these many parameters of rectifiers, we must know how to calculate them. We must know their mathematical expressions from the exam's point of view. This is very important. From rectifiers, around 10 to 12 marks questions might come in your final exams. Now the next topic that comes is clippers. Clippers, name itself implies it clips something, and clipping means to remove some particular portion of the input waveform. So what does a clipper do? Clipper removes some particular portion of the input waveform without distorting the remaining part. So clippers are the circuits which remove some particular portion of the input signal without distorting the remaining part. Now they are of various types: positive clipper, negative clipper, biased clippers. Positive clipper, negative clipper, biased clippers, combination clippers, and we also have miscellaneous clippers. So when you have so many clippers types, you need not cram each and every clipper. You must know the method, how to solve the circuit of a clipper. So only the method is what matters. Only the method is important to understand. It's not necessary that you cram and learn each and every clipper. You must know how to solve or analyze the circuit of a clipper. So I will show you one or two very important circuits, how to analyze. Pay attention to the method that I am implementing over here. Okay. So first of all, I will take a very simple clipper, that is positive clipper. Okay. So let me take this clipper. I am taking a shunt type clipper. In the next part, I will also take a series clipper, so don't worry for that. I'll try to cover each and every type of clipper over here, but pay attention only to the method. So this is the clipper circuit, shunt type, positive clipper. This is the input signal that you have given. Now let's see what does this clipper do to this particular input signal. So how to analyze is, the first step is, first of all, you analyze the circuit in the positive cycle. So during positive half cycle, during positive cycle. So the first heading should be this. Now the second step should be to put the signs. So when you are considering the positive cycle, put plus minus. All right, like this. Now let's see what is the status of the diode. Diode is forward or reverse. So keep your pens on the diode. Diode P part. Now diode P part is getting positive. Diode N part is getting negative. So diode is forward. Write it down. Don't apply any shortcut. Diode is forward. Forward means short circuit. Reverse biased diode means open circuit. So because this diode is forward biased, so it is a short circuit. Short circuit means we have replaced it with a simple wire. And now our objective is to calculate V naught. So V naught, just pay attention. Just keep your eyes on V naught. What is V naught? V naught is between these two terminals, all right? And between these two terminals is connected a simple wire. So that means when you will put the multimeter across these two wires, जहाँ पर डायोड था, अगर आप वहां पे मल्टीमीटर लगाओगे तो वहां पे तो अब सिंपल वायर है, आपने उसको शॉर्ट सर्किट कर दिया है, तो वी नॉट किसके बराबर आ जाएगा? द वोल्टेज अक्रॉस अ शॉर्ट सर्किट इज 0, सो वी नॉट इज इक्वल टू 0. Is it clear? I hope it is clear to everyone. So V naught is equal to 0. अगर ये ब्रांच होती ही ना, अगर डायोड को हम ओपन कर देते, अगर डायोड रिवर्स होता, इफ द डायोड वुड हैव बीन रिवर्स्ड, इट वुड हैव बीन रिप्लेस्ड बाय एन ओपन सर्किट, दैट मीन्स ये ब्रांच यहाँ से गायब होती, ये होती ही ना. तो फिर आप वी नॉट को कैसे मेजर करते? फिर ये ब्रांच जब यहाँ पर है ही नहीं, तो अब जो वी नॉट होता वो वी आई के इक्वल हो जाता. क्यों हो जाता? क्योंकि जब आप इस लूप में केवीएल लगाते तो वी नॉट इज इक्वल टू वी आई प्लस आई आर आता. आई जीरो है क्योंकि इसमें ओपन सर्किट होने के कारण करंट जीरो है, तो आई आर वाला पार्ट जीरो हो गया, तो वी नॉट इज इक्वल टू वी आई. लेकिन अगर ये ब्रांच एग्जिस्ट कर रहा है तो हमें मल्टीमीटर इसी ब्रांच के अक्रॉस लगाना होगा, क्योंकि वही उसी ब्रांच के अक्रॉस जो वोल्टेज है वही वी नॉट है. इज इट? आई होप आई एम क्लियर. So V naught is 0. Now during negative cycle, अब हमने V naught निकाल लिया, so the first step is over. Now during negative half cycle, so the first step is to write the heading, then the second step is to put the signs. Don't struck off the previous signs. Put these signs in the bracket, minus plus like this. Put your pen on the diode. The P is getting negative, N is getting positive. Diode is clearly reverse biased. Reverse means open circuit. Open circuit means that the diode branch, it does not exist now. The branch is lost. ये जो branch है अब गायब हो चुकी है. Now, what is the method to calculate V naught? Apply KVL in the circuit. Why I am saying that apply KVL? I am not saying that V naught and VI are in parallel, because जब तक उनके बीच में R रहेगा, V naught VI कभी भी parallel में नहीं हो पाएंगे, है ना? तो पैरेलल में वोल्टेज सेम होता है, आर वोल्टेज सेम नहीं होने देगा. आंसर वी नॉट का भले ही वी आई आ रहा है, लेकिन ये दोनों पैरेलल में हम नहीं कह सकते क्योंकि बीच में आर लगा हुआ है. तो इसलिए केवीएल लगा रहे हैं, क्योंकि वी नॉट इज इक्वल टू वी आई प्लस आई आर आएगा. आई आर जीरो हो जाएगा क्योंकि करंट जीरो है ओपन सर्किट के कारण, तो वी नॉट इज इक्वल टू वी आई. Concepts should be clear. So V naught is equal to Vi. We are done with both the V naughts in both the cycles. Now let's draw the output waveform. Output waveform, for the output waveform, first of all, let's prepare the axis. Separate the positive and negative cycles. For the positive cycle, answer is 0. For the negative cycle, answer is the answer is minus Vi. I'm sorry. Minus Vi, because when you will apply the KVL, you will get plus V naught plus Vi plus IR is equal to 0. V naught is equals to minus Vi. Alright, so minus Vi is drawn over here. This is minus Vi. Draw it as it is. So we have clipped off the positive cycle. Follow the method. Okay. I hope the method is clear. Now let us see another circuit for a negative clipper. And in this case, I am taking the series circuit. So here the V naught is across R. That means whatever voltage will be developed in R, that will be V naught. Now again we have input waveform like this. So first step was during positive cycle, put the signs. Diode is forward biased. That means short circuit. When it is short circuit, that means the current will flow. Now our eyes should be on V0. V0 is across R. When the current is flowing in R, means we will be getting IR value, that means we will be getting some V0. So V0 here is, you can apply KVL, just that the voltage across R is V0. So you can instead of writing IR, you have to write V0, then only you will be getting it in the equation and you will be able to calculate it. So when you will apply KVL, V0 will be equal to Vi. Now during negative cycle, put the signs like this. Then we have diode is reverse biased, that means open circuit. Due to the open circuit, current in the circuit is 0. That means no current is going to flow in R and voltage across R will be 0. So V0 is equals to 0. So now how to draw the output? Prepare the axis, separate the cycles. For the positive cycle, you have answer Vi plus Vi, draw it as it is. For the negative cycle, you have 0, draw it. So this is negative clipper. Okay, so this is how we solve the clippers. You have to follow the method properly. You don't have to see each and every type of clipper, that how this clipper works, how that clipper works. You just need to follow the method. Now I'll show you a very important clipper, that is biased clipper. The questions that usually comes in the exam, but the method is going to be the same with a little change, because this time when we are talking about bias clipper, we will be including battery in the output. We will be including battery in the circuit. So let's see a question. This is 5-volt battery. Let's draw the input waveform. This is given 20 volt maximum value. Okay, so now let us start. So the first step always is during positive cycle, put the signs. The signs are already there, plus minus. Now put your pens on the diode. Diode P is getting negative of the battery. Alright. N is getting also negative of Vi. So when both the P and N are getting the same signs, then it is not possible to decide whether the diode is forward or reverse at once. So what you have to do, you have to make two cases. Case 1, and after 4 lines you have to write case 2. Without looking to the diagram now again and again, just make two cases. The first case will be always and always P greater than N. The second case will be always and always P less than N. P greater than N will be always forward. P less than N is always reverse. I am not looking to the diagram again and again. Once I have seen that the diode P and N are getting the same signs, I have not looked at the diagram again, and I am not getting confused by looking into it again and again. I just made two cases. Case 1 after 4 lines, case 2. Case 1 is always P greater than N. Case 2 is always P less than N. P greater than N always forward, P less than N reverse. Because P greater than N means that the potential of P is greater than potential of N. So that case is always forward. Now you just leave 2 lines and write down V0 for both the cases. Now go to the diagram again. For the first case, without thinking or without giving the thought to any other thing again, just make your diode forward. Forward means short circuit. So I am doing my diode short circuit. I am replacing it with the short circuit in my mind. So डायोड की जगह अब एक सिंपल वायर आ चुका है, शॉर्ट सर्किट हो चुकी है डायोड. नाउ आवर ऑब्जेक्टिव इज टू कैलकुलेट वी नॉट इज हियर, एंड फॉर दैट वी विल बी अप्लाइंग केवीएल. अगर डायोड ओपन होती तो यहाँ पे आर में कोई करंट फ्लो ही नहीं करेगा, वोल्टेज कुछ डेवलप ही नहीं होगा और वी नॉट जीरो हो जाएगा. लेकिन जब डायोड शॉर्ट सर्किट है तो करंट पूरी तरीके से सर्किट में फ्लो कर रहा है, और अब हमें वी नॉट को कैलकुलेट करना पड़ेगा क्योंकि उसका कुछ वैल्यू है. तो उसके लिए हम लोग केवीएल लगा रहे हैं. केवीएल का क्या इक्वेशन बनेगा? प्लस वी नॉट माइनस वी आई प्लस 5 is equal to 0. So V naught is equal to Vi minus 5. So the answer is Vi minus 5. Now for the second case, अगर हम V naught निकाले तो V naught डायोड रिवर्स है, ओपन है, R में कोई करंट नहीं है, V naught 0. This part is done. Now the second step is to write the values of P and N in the same manner as you write it in your maths. So put the value of P, put your pens on the P and see what the P is getting. It is getting minus 5. Greater than N. What is N getting? Minus Vi. And now, without looking to the diagram, you can even write minus 5 less than minus Vi. In order to remove this minus sign, use the inequality equations of maths and it will get converted like this. Similarly, it will get converted like this. So this is how we implement the method in order to solve a biased clipper. So in the case of biased clipper, it is very much probable that in one of the cycles, your diode P and N type will be getting the same signs. So whenever P and N gets the same sign, just make two cases and solve the question. Now, here the positive half cycle part is done. Now let us see for the negative half cycle. During negative cycle, put the signs without strucking off the previous ones. Put your pens on the diode. P is getting negative, but your N is getting positive. So diode are getting, P and N are getting opposite signs. You can decide whether the diode is forward or reverse. It is reverse at once and it is open circuit. When the diode is open circuit, V naught is again 0 because V naught is the voltage across R and no current flows in the R. So V naught is 0. Now we have calculated V naught for both the cycles, so our calculation part is over. Let's draw the output waveform. For the output waveform, now first of all prepare the axis, separate the cycles. And before proceeding over to the output waveform, first of all, if the clipper circuit is a biased clipper, then you must show the battery in the input cycle. So the battery is of 5 volt plus 5 volt because moving from left to right, the battery is having positive terminal first, so it is a positive battery. So we will be showing a positive 5 volt over somewhere here. Now for the positive cycles, as you can see, you have two answers. That means you have two regions. So wherever the battery cuts their positive cycle, just make two lines from there. So the battery is cutting the positive cycle on two places, as you can see over here and here. So I have made two lines over here. And this will always be the case. The battery will only cut at two places. Alright, now the middle portion is the cap portion where Vi is greater than 5 volt. See, I'll highlight it with the green pen. This middle portion is the cap portion where Vi is greater than 5 volt. So where is Vi greater than 5 volt? Just come over here in the calculation. Here, Vi is greater than 5 volt. And the answer over here is Vi minus 5. So what was Vi over here? Vi is this. Now I am showing it with a red pen. Vi is this. And you have to do minus 5 also over here. So minus 5 means that this particular cap will shift with minus 5. तो इसका स्टार्टिंग और एंडिंग पॉइंट देखिए, स्टार्टिंग पॉइंट 5 है, उसमें माइनस, तो यानी वी की जगह आप उसकी स्टार्टिंग और एंडिंग पॉइंट्स रखो। तो वी शुरू कहाँ से हो रहा है, 5 से, तो 5 माइनस 5 जीरो पर आ जाएगा, क्योंकि उसको शिफ्ट करना है जीरो पर, सॉरी -5 से। और कैप का एंडिंग पोर्शन कहाँ तक जा रहा है, 20 तक, तो 20 माइनस 5 कहाँ पर आकर रुकेगा, 15 पर। शेप यही रहेगा, क्योंकि वी नॉट का आंसर है वी की टर्म्स में, वी-5, तो शेप तो वी का ही रहेगा, लेकिन वो वी का जो शेप है वो शिफ्ट कर गया -5 से। शिफ्ट करने के लिए मुझे वी का स्टार्टिंग और एंडिंग पॉइंट चाहिए था। स्टार्ट हो रहा था ये पोर्शन 5 से, तो 5 माइनस 5 जीरो पर आ गया, और जा रहा था 20 तक, तो 20 माइनस 5 15 पर आ गया। तो शेप यही रहेगा, शुरुआत 0 से हुई, गया 15 तक। बाकी के पोर्शन में आंसर इज 0, as you can see in the calculation. So answer is 0. Negative cycle में answer is again 0. So this is how we draw the waveform. Very, very important. Just listen to this particular part. By rewinding the video again and again, you will surely understand that how to calculate and draw the waveform for the biased clippers. I hope I am able to convey the information properly. Now let us move on to the next part, that is clampers. As this is a one short video, so we need to cover the topics quickly, और ये मॉड्यूल है भी बहुत बड़ा, तो इसीलिए हम थोड़ा सा जल्दी कवर अप कर रहे हैं। बहुत डिटेल में अगर आपको देखना है तो आप क्लिपर्स की सेपरेट वीडियो भी देख सकते हैं। आई विल शेयर द लिंक इन द डिस्क्रिप्शन बॉक्स। नाउ लेट अस कम ऑन टू द क्लैम्पर्स। सबसे पहले क्लैम्पर्स का मतलब समझते हैं। तो क्लैम्पर्स वो सर्किट्स होते हैं जो बेसिकली किसी भी इनपुट वेवफॉर्म को एक पर्टिकुलर वैल्यू से केवल शिफ्ट करते हैं। ठीक है, फॉर एग्जाम्पल वी आर हैविंग अ सिग्नल लाइक दिस। तो केवल जब हमें इस सिग्नल क्लिपर्स में हम इस सिग्नल की कटिंग करते थे, यानी हम इस सिग्नल का कोई भी पोर्शन कहीं से भी रिमूव कर सकते थे। लेकिन क्लैम्पर्स में बात बहुत सिंपल सी है, एंड द सिंपल थिंग इज दैट वी आर ओनली गोइंग टू शिफ्ट दिस सिग्नल, वी आर ओनली गोइंग टू शिफ्ट दिस सिग्नल बाय अ पर्टिकुलर वैल्यू। हम केवल इस सिग्नल को शिफ्ट करेंगे एक पर्टिकुलर वैल्यू से। जब हम शिफ्टिंग की बात करते हैं तो हम केवल सिग्नल की टॉप वैल्यूज या बॉटम वैल्यूज से ही बात करते हैं। We only deal with the top and the bottom values when we are concerned with the shifting of signal. So this clamper circuits are going to be very simple to analyze, because here you are only going to deal with the top and the bottom values of the signal, because here in this particular case we are only going to shift the signals. I hope I am clear at this particular point. So let us see clamper. First of all, clampers को एनालाइज करने का प्रोसेस अलग रहता है, और जब हमें वो प्रोसेस अप्लाई करना है तो उसकी पहचान ये है कि क्लैम्पर्स के सर्किट्स में कैपेसिटर प्रेजेंट होता है। तो क्लैम्पर्स के सर्किट की पहचान है कैपेसिटर्स का प्रेजेंस। सो जब भी किसी सर्किट में कैपेसिटर प्रेजेंट होगा, हमें समझ जाना है दैट वो सर्किट क्लैम्पर का है। ठीक है, तो लेट अस सी अ क्लैम्पर सर्किट। Diode, capacitor, Vi, R and V0। कैपेसिटर की प्रेजेंस से हम लोग समझ गए कि ये क्लैम्पर का सर्किट है। नाउ वी हैव टू फॉलो सर्टेन स्टेप्स। द फर्स्ट स्टेप इज कि हमें उस साइकिल से शुरुआत करनी है जो साइकिल इस डायोड को फॉरवर्ड कर रहा हो। We have to start with that particular cycle which makes this diode forward biased. So keep your pens on the diode, N को दीजिए नेगेटिव और P को डायरेक्टली दीजिए पॉजिटिव। क्लिपर्स के केस में बायस्ड क्लिपर्स जब हम पढ़ते थे तो जब बीच में बैटरी आ जाती थी तो उसका बहुत इंपॉर्टेंट रोल होता था, लेकिन यहाँ पर बैटरी का रोल बहुत ज़्यादा नहीं है। आपको यहाँ पे कभी भी दो केस बनाने नहीं पड़ेंगे, क्योंकि यहाँ पे डायरेक्टली यू हैव टू डील विद दी VI वैल्यूज Alright, so don't pay attention to the battery when you are looking whether the diode is forward or reverse. बैटरी का काम केवल तब लाइट में आएगा जब आप KVL लगाओगे, तो बैटरी बीच में आएगी। डायोड फॉरवर्ड हो चुकी है। डायोड के फॉरवर्ड होते ही करंट कंडक्शन होगा। करंट कंडक्शन होगा तो कैपेसिटर भी चार्ज होगा। अब हमें कैपेसिटर का चार्ज निकालना है। तो पहला स्टेप था, हमें उस साइकिल से शुरुआत करनी है जो डायोड को फॉरवर्ड करे। सेकेंड स्टेप इज हाउ टू second step is to calculate the voltage of capacitor. That means we have to calculate VC. और जब VC कैलकुलेट करने की बारी आई तो हमें VC की पोलैरिटी भी पता होनी चाहिए, तभी हम KVL लगा पाएंगे और VC निकाल पाएंगे। उसके लिए डायोड में आपने करंट को चलवा दीजिए, क्योंकि डायोड के थ्रू ही करंट फ्लो होगा और डायोड में करंट फ्लो करता है P2N। डायोड में करंट चलेगा, जहां पहले एंटर करेगा कैपेसिटर में वहां प्लस, जहां बाद में एंटर करेगा वहां माइनस। अब इस लूप में हमें KVL लगाना है। फॉर एग्जाम्पल VI का टॉप वैल्यू था 20 वोल्ट और बॉटम वैल्यू भी है -20 वोल्ट। सो नाउ अब KVL लगा देना है। KVL लगाने पर प्लस VC माइनस VI माइनस 5 इज इक्वल टू 0। VC is equals to VI plus 5. Now put the value of VI over here. In the case of clippers, we were not allowed to put the value of VI, क्योंकि VI का जो मैक्सिमम वैल्यू था वो पूरे साइकिल का वैल्यू नहीं था। लेकिन यहाँ पे शिफ्टिंग करनी है तो यहाँ पे आप VI की जगह टॉप और बॉटम वैल्यूज पुट कर सकते हैं। तो VI जो यहाँ पे अब आप पुट करेंगे, दिस वाज द केस ऑफ नेगेटिव साइकिल। नेगेटिव साइकिल पर जाइए इनपुट्स के और उसका टॉप VI देखिए कि उसका पीक वैल्यू कहाँ पर है। इट इज -20 वोल्ट। माइनस साइन को नेग्लेक्ट करिए, क्योंकि ऑलरेडी जब आपने साइकिल्स का निशान लगाया माइनस प्लस तो वो माइनस कंसिडर हो चुका है, तो आप केवल मैग्नीट्यूड रखिए। तो VI की जगह हम बॉटम वाला 20 रख रहे हैं, टॉप वाला नहीं। बॉटम वाला 20 प्लस 5, दिस इज 25 वोल्ट। तो VC कभी भी नेगेटिव में नहीं आता, VC always comes in a positive answer, so it is 25 volt over here. अब now third step is to calculate V naught. जब हम नेगेटिव साइकिल में चल ही रहे हैं तो साथ साथ V naught निकालते चलेंगे। डायोड हमने फॉरवर्ड कर रखी है, यानी शॉर्ट सर्किट है, लेकिन इस ब्रांच में अब बैटरी बची है +5 वोल्ट की, तो जो ब्रांच का वोल्टेज है वही R का है और वही V naught है, क्योंकि आप देख सकते हैं तीनों पैरेलल में है। तो V naught is equals to +5 वोल्ट। तो नेगेटिव साइकिल में के थ्रू हमारे दो काम हुए, VC भी निकल गया और V naught भी नेगेटिव साइकिल का आंसर आ चुका है। अब बची है पॉजिटिव साइकिल, यानी यहाँ पर क्लैंपर्स के केस में, क्लिपर्स के केस में तो हमेशा हम पॉजिटिव साइकिल से शुरुआत करते थे, लेकिन क्लैंपर्स के केस में आप जरूरी नहीं कि हमेशा पॉजिटिव साइकिल से शुरुआत करेंगे, आप उस साइकिल से शुरुआत करेंगे जो डायोड को फॉरवर्ड करेगा। Now during positive cycle, put the signs in the brackets without strucking off the previous signs. Diode is reversed, surely no two cases will be formed over here. Just look to the signs of VI. Diode is reverse, that means open. ओपन सर्किट के साथ लगी बैटरी भी ओपन होती है, यानी ये पूरा ब्रांच यहाँ से गायब हो चुका है। अब जो V naught है वो R के क्रॉस है, और अब हमें इस लूप में क्या लगाना होगा, KVL, तभी हम V naught को निकाल पाएंगे। तो जब V naught निकलेगा वो कैसे निकलेगा, V naught is equals to KVL लगाने पर -VI। VC की पोलैरिटी नहीं बदलेगी, once you have fixed the polarity of VC, it's not going to change. Minus VC is equal to 0. So V naught is equals to VI plus VC. VI is again 20, but this time it is the top 20 wala part plus VC, that was 25, and the answer is 45 volt. Now let's draw the output waveform. We have calculated the V naught for both the cycles. Separate the cycles, prepare the axis. For the positive cycle, अब आपका आंसर क्या आ रहा है पॉजिटिव साइकिल में 45 वोल्ट, यानी जो वैल्यू पहले 20 पर थी अब वो किस पर शिफ्ट हो चुकी है, +45 पे, यानी जो शिफ्टिंग है वो +25 की है। तो जब +25 की है तो अब आपको तीन वैल्यूज में 25 वोल्ट ऐड करना है। आपने ऊपर की 20 में जब ऐड किया 25 तो बना 45 जो कि आंसर था। जीरो में भी ऐड करिए, जीरो मिडिल एक्सिस में वो 25 पर आ गया, और -20 + 25 विल गिव यू +5 वोल्ट, यानी सारी चीजें एक्स एक्सिस के ऊपर जा चुकी हैं। शेप बिल्कुल सेम रहेगा, जीरो एक्सिस यहाँ पर है, 25 पर आ चुकी है, तो जो जीरो एक्सिस आपने नीचे बना रखी थी डॉटेड लाइन से उसको ऊपर बनाइए। शेप को सेम रखते हुए पॉजिटिव पीक को 45 वोल्ट से टच कराइए, नेगेटिव पीक को 5 वोल्ट से टच कराइए। I'll again draw the output waveform once again. आपने देखा कि जो पॉजिटिव साइकिल का आंसर है वो है 45 वोल्ट। पहले ये वैल्यू 20 वोल्ट पर थी, यानी शिफ्टिंग +25 की हुई, तो अब आपको तीन वैल्यूज में 25 ऐड करना है। टॉप वैल्यू में 25 ऐड किया, 45 बन गया। मिडिल यानी जीरो एक्सिस में 25 ऐड किया तो 25 बन गया, 0 + 25, और -20 + 25 किया तो +5 वोल्ट बन गया। जीरो एक्सिस मिडिल में आई, शेप सेम रहा, पॉजिटिव पीक 45 पर टच किया, नेगेटिव पीक 5 वोल्ट पर टच किया। Shape is going to remain the same. So this is how we solve the clamper. Clampers are very easy to solve once you listen to the video and to the steps carefully. Pay attention to the method. Don't pay attention to the circuit. Pay attention to the method and clarify your concepts. So I hope that I am able to convey the concept of clampers in a proper way. Now let's move on to the next topic, and that is voltage multipliers. Voltage multipliers. First of all, let us understand the concept. First of all, voltage multipliers gives the output in the form of DC. So input is AC, output is DC. So what is the difference between rectifier and multiplier? Rectifier simply converts AC into DC, but voltage multipliers are those circuits which generate a DC output value whose value is multiple of the peak AC input voltage. Very important. So because it is a multiplier, so definitely it's going to generate some multiples. Multiples of what? Multiples of the peak AC input voltage. That means if you have applied an AC input voltage of Vm sin omega t, then it would be able, voltage multipliers will be generating 2 Vm, 3 Vm, 4 Vm, and so on. We only go up to 4 Vm because after 4 Vm it starts generating distortion also. So we go up to doubler, tripler, and quadrupler. So this is the concept of voltage multiplier. Now I'll try to convey the voltage multipliers are very easy to understand. So I will be directly explaining the tripler and quadrupler circuit where you will be coming across doublers also. So in only a single circuit, we will be having doubler, we will be having a tripler, we will be having a quadrupler. But voltage doublers, if we talk about voltage doublers, we have full wave voltage doubler and half wave voltage doubler. So you can learn them separately from the video. I'll share the link in the description box. But it's important to understand in this one short video, it is important to understand the concept of voltage multipliers, which I will be conveying through the very general circuit of voltage multipliers. So we all know that voltage multipliers is going to convert AC into DC. For AC, we will be needing a transformer. Here is the transformer. Now, the way to learn is draw a capacitor over here and a diode like this. So this is called one peak circuit. Peak circuit is the combination of capacitor and diode. If you want to generate 2 Vm, that means doubler, you need to put 2 peak circuits. If you want to generate 3 VM, then you need to implement 3 peak circuits. And if you are going to achieve 4 VM, then you need to implement 4 peak circuits. So here we will go up to 4 VM. We will be having 4 peak circuits. So one is like this, C1, D1. Now another peak circuit will be, capacitor will be in the alternate position and the diode will be in the opposite direction. That is C2, D2. I hope it is easy to understand. Then again the capacitor will be here, diodes will be reversed, C3, D3. And the last peak circuit, that is C4, D4. Very easy to learn this circuit. We have Vm sine omega t over here, that is AC voltage. Now for the positive cycle, diode D1 will be forward and D3 will be forward. You can easily see that. And whichever diodes will be forward biased, their particular associated capacitors will charge. So here, as D1 is forward biased, therefore capacitor C1 will charge, and we all know that C1 will charge up to the peak value. So the peak value of in this particular loop, when you will apply KVL, you will be getting, and as in the case of clampers, you understood how to calculate VC1. Polarity will be like this because the diode direction is like this. Current is flowing in P2N. So keep the current flowing. Wherever the current will enter first, it will be having a positive sign, and wherever the current will enter in the latter part, it will be having a negative sign. So when you will calculate VC1 by applying KVL in this loop, you will get VM because we are taking the peak value. We all know that the capacitor charges up to the peak value. हमने C3 को अभी चार्ज इसलिए नहीं किया क्योंकि हमें C2 चार्ज अभी नहीं पता है. C2 चार्ज जब तक नहीं पता होगा तब तक C3 भी चार्ज नहीं होगा. तो अभी केवल फर्स्ट पॉजिटिव हाफ साइकिल में C1 चार्ज हुआ. अब जब नेगेटिव हाफ साइकिल आया, नेगेटिव हाफ साइकिल में डायोड D2 फॉरवर्ड होगा और कैपेसिटर C2 चार्ज करेगा. कैपेसिटर C2 के चार्ज होते ही यहाँ पर फिर हम लोग KVL लगाएंगे. KVL लगा करके आंसर आएगा 2 VM. So in the similar manners, जैसे जैसे हम लोग पॉजिटिव साइकिल्स में आगे बढ़ते जाएंगे, अब जब दूसरा पॉजिटिव हाफ साइकिल आएगा तो D3 फॉरवर्ड होगा और C3 चार्ज होगा. अब ये पूरा लूप बनेगा और यहाँ पर आप KVL लगा सकते हैं. तो C3 का जो भी चार्ज आएगा, that will be equal to 2 VM again. That will be 2 VM again. Again C4 will be 2 VM. So this is how the voltage multipliers work. That means if you are calculating the voltage across this particular part, you will be getting 2 VM. If you will calculate the voltage across the whole part, you will be getting C2 plus C4, that is the voltage, sum of the voltage of C2 and C4, that will be 4 VM, that means the quadrupler. And if you will calculate the voltage across this particular section, you will be getting VM plus 2 VM, that is voltage tripler. So this is voltage multipliers. Now in the last part of this particular module, we have some two terminal devices like LED, light emitting diode. We all know that the operation of LED, principle of operation is that this diode works in the forward biased region. That means whenever you will forward bias this diode, the diode will conduct current and the light will be emitted. So by the process of recombination, because we have seen that when recombination takes place, energy is released either in the form of heat or light. So in the case of LED, it is made up of such type of semiconductor materials that whenever recombination takes place, light is emitted in the form of, energy is released in the form of light. So it is not made up of silicon or germanium. In fact, the most popular material from which the LED is made up of is gallium arsenide phosphide. And in this particular material, whenever recombination takes place, energy is released in the form of light. Another is varictor diode. Varictor diode is, the name has come from variable capacitor, and the symbol is like this. And the symbol is like this. So this is varictor diode. It works in the reverse biased region, and the depletion layer of the reverse biased region behaves as the dielectric over here. Capacitance is given as epsilon A by D. This is mainly used for tuning of these things. Whenever you will increase the reverse bias, the depletion layer will increase. That means D will increase, capacitance will decrease. So we can also draw a graph between diode capacitance and reverse voltage, because it only works for reverse bias. So as you are increasing the reverse bias, depletion layer is increasing and capacitance is decreasing. So this is mainly used in tuning circuits, radio, television, basically for tuning purposes. We have also tunnel diode. Tunnel diode, the special thing about tunnel diode is that in the case of tunnel diode, first of all, let us see the symbol. This is tunnel diode, and it is fabricated by doping the semiconductor materials up to 100 to 1000 times more than that of a normal PN diode. So the doping over here is very, very high, and a very high doping results into a very reduced depletion layer. So as soon as you forward bias this diode, it does not wait for the potential barrier. In fact, it reaches up to the maximum current. Therefore, it is used in very high speed computers. All right. So this is the characteristic region for the tunnel diode. So these are the important points about these various two terminal devices which we must remember. So I hope that this one short video might help you during the exams for module 1, and keep learning and do refer the concepts properly through this video as well as through the links that I will share in the description box. So thank you all. Thank you, learners.